Welcome friends to the course of marketing research and analysis. Well, we have been covering the non-parametric test for the last few classes, around 6-7 classes. So, we have seen why non-parametric tests are so useful, right? What is the importance of non-parametric test and why they should be used in research studies. Basically, in most of the classrooms I have seen teachers tend to do the statistical test based on the on normal data, right. But we ignore the data which is not normal. So, their non-parametric tests come of great importance, great value, right. So, we have seen, for example, when the data is not normal, you can convert the data to a normal data, right. So, if the data is not normal, so you can if the data is skewed to the right or left whatever, so or it is a kurtotic data, then you can convert the data and make it look like a normal data. So, what does a normal data mean? The central tendency, the mean median mode lie on the same line, right, in the center. But if suppose you convert the data into a normal data and you do it, then well and fine, but if the data is still not normal, is not behaving normally, it is still a skewed data, right. So, maybe if you make a histogram, something the data, it looks something like this, right. So, if you see, if this is the pattern of data, then you will not say, if you take a path, then you cannot say this data is a normal data, right. So, when the data is not normal, it could be for many reasons, one of them being the presence of outliers, right. So, outliers can affect the data. So, we have seen that, and when your data is a non-normal data, so you use non-parametric test, and you have similar non-parametric tests as you have for parametric tests. So, for example, when you have one group only, one sample, then we say one group, for example, then we say we use a one sample test, right, one sample test. So, here on the other hand, when you do a non-parametric test, you do a KS test basically, right. So, the one sample test helps you to find out whether the population and the sample, they are connected or they are related or not. Similarly, the KS test also helps you to check normality, and it helps you to find out whether the sample is part of the population or not, right. You have the independent sample t tests, right, independent sample t test. So, in when you have independent sample t test for two groups, right, in the non-parametric you have a Mann-Whitney test, right, similarly, right, Mann-Whitney Wilcoxon test. So, the Mann-Whitney test exactly does the same work what the independent sample t test does, but the point is here the data is not normal and here the data is a normal data. So, these things we have seen. For example, you have a paired sample t test for the same sample group, but done maybe twice. So, to do that, you have in this case you have a Wilcoxon test, right, a Wilcoxon test. So, the Wilcoxon test helps you to do the same thing, right. When you have more than two groups, we said it is a case of 3 groups. So, is a one way ANOVA. So, instead of a one way ANOVA for the non-parametric case, we have a Kruskal-Wallis. So, Kruskal-Wallis, right. Then we said what happens if my data has repeated measures, right, that means the same respondent are being repeated twice, thrice, 4 times. So, the sample remains the same. So, what will I do in this case? So, you have a one way ANOVA with repeated measures, right. Similarly, you have a Friedman's test, right, for this. So, there are several things which you can see making it similar to the parametric ones, the non-parametric and the parametric. So, one test such test which out of what we have done, for example, we have done the chi-square test, which is a very powerful test, the McNamara test, the Mann-Whitney, Kruskal-Wallis, the the sign test, the runs test. The runs test is a test which I had already said. So, since I am recapping, I am trying to tell you again. So, the runs test was a test where we are trying to check the randomness, the occurrence of a variable, right. If the variable or the product or anything, that is it occurring in a systematic manner or it is coming in a random manner. Suppose it is coming in a systematic manner, if it is coming in a random manner, then it is okay, no problem. But if it is a systematic occurrence is there, then we would try to understand why this is happening systematically. Is it because of some problem in the machine or some problem in the understanding, what is happening here. So, these are some of the tests which are very helpful, at least for example, the runs test is very helpful in a quality control case. So, when the data when the researcher is trying to do a quality control test, in that kind the runs test is very important. Okay. So, today what I will do is we will wind up with one of the last tests that I should have done earlier also, but no issues, we will do it now. So, this is the Kolmogorov-Smirnov KS test. So, this test you must have seen if you are using you are working on the SPSS or any data set database, then you will see the software packages. This is always attached with the Shapiro-Wilks test, the Shapiro-Wilks test, right. You will find it with the Shapiro-Wilks test. Now, these tests are used for normality checking, normality check, right. So, what it basically does is it helps you to check the normality of the data, tells you whether the data is coming from the same population or not, the sample is coming from the same population or not, let us say. So, what is this KS test? It is a simple non-parametric method for testing whether there is a significant difference between an observed frequency distribution and a theoretical frequency distribution. I have repeated it many times that whenever you have an observed set of data and you have an expected set of data, so then the data, if there is a lot of difference between the two sets, then what happens, then we will assume that the model is a weak model or is not a fitting model, right. But if the observed frequency and the expected frequency is close, then we will say the model is very is actually behaving what it should be like, what it should be doing, right. So, the difference, the lower the difference, the better it is, right. If it is low, it is good, if it is low, it is a good thing, right. But if it is high, then not good, right, not good. So, the KS one sample test is more powerful than the chi-square, since it we are talking about non-parametric test, and chi-square being one of the most powerful chi-square non-parametric follows a chi-square distribution, right, which is a right tailed distribution, right skewed distribution. Since it can be used, why it is powerful? Because it can be used for small samples, which chi-square does not permit you sometimes, right. So, unlike the chi-square, this test is a test which can be used for small samples. Now, what is the null hypothesis in this case? The null hypothesis assumes that no difference exists between the observed and the theoretical distribution. Now, what do I mean by the observed? I just said you have some observed values, right, you have some expected or the theoretical, expected or theoretical, right. So, this is what you expect. So, this values that comes, let us say whatever values you get, now this it says that there is no difference, we are saying no difference. Now, just imagine if there is no difference, that means what? It is the observed and the theoretical are more or less the same, right, okay, fine. So, and what we calculate is the observed and the theoretical distribution, and the value of test statistic which is given as D, right. D is calculated as D is equal to the maximum value that occurs when you subtract the expected frequency distribution and the theoretical frequency distribution. So, FOX or F0x is equal to observed cumulative frequency distribution of a random sample of n observations. So, there are n observations. Now, what is the frequency distribution of this random sample of n observations is called my F0x. So, F0x is given by k by n, where k is what? Now, k is the number of observations, right, number of equal to or less than x, equal to or less than x. Now, and n is my total number of observations. So, and what is FRX is the theoretical frequency distribution. So, this is the expected, right, under H0. So, the critical value of D, the difference, right, is found from the KS table values for a one sample test, we will see that. Now, the acceptance criteria is same again, like what you have to do, when your calculated value is more than the table value, it goes away from the table value, then we, if the calculated value is less than the critical value, we accept. That means what? If you remember, if this is my, let us say table value and this is my calculated value, this is going out. So, this is a rejection case, but if the calculated value falls here, then it is a acceptance case. Okay. So, acceptance criteria is if calculated value is less than the critical value or table value, right, accept the null hypothesis. If calculated value is greater than the table value, we reject the null hypothesis. Okay. Now, take an example. Let us take an example and understand the case test. Okay. This is a study done for 60 college students of various streams, okay, with equal number of students drawn from each stream. Are we interviewed and they are interviewed and their intention to join the drama club of the college was noted. Okay. So, number in each class from BSc is Bachelor of Science, 5 students came, Bachelor of Arts 9 students, Bachelor of Commerce 11 students, Master in Arts, Master of Arts 16 students, Master of Commerce 19 students. But it was expected that 12 students from each class would join the drama club, but actual figure is the observed frequency is not same, it is 5, 9, 11, 16, 19. So, this is more than the 12, this is much less than the 12, right. So, can we infer something? Now, what is the null hypothesis in this case? There is no difference, there is no difference among students of different streams with respect to their intention of joining the drama club. So, as you had expected that they all would be equal 12, 12, 12, 12, 12, but then the observed is different, but then your null hypothesis says there is no difference, the observed and the expected are the same. And what is the alternative? Obviously, there is a difference between the observed and the expected frequency. So, we develop the cumulative frequencies for observed and theoretical distributions. Now, let us go. So, the streams are BSc, BA, BCom, MCom up to MCom. Number of students interested in joining. So, observed is my O is my observed frequency. So, we have it already. So, n is equal to how much? 60. So, 5 plus 9 plus 11 plus 16 plus 19 is 60. Okay. My theoretically I expected that at least 12 will come from each class, right. So, I said 12, why 60 divided by 5, so is equal to 12. So, 12, 12, 12, 12, 12. Now, what is my observed frequency now? The cumulative frequency. The first is 5 by 60. So, 5 upon 60 plus this. So, 5 by 60 plus 9 by 60 is 14 by 60, then plus 11 by 60. So, that comes 25 by 60, then I have plus 16 by 60, right. So, that gives me how much? 25 plus 16 is 41 by 60, right. So, 41 by 60 and lastly this is 60 by 60. So, we have got this. Okay. Now, what is my theoretical distribution at 12 by 60? Second theoretical cumulative. Next is 24, 12 plus 12, 12 plus 12 plus 12 plus 12. So, 12, 24, 36, 48 and 60. Okay. So, what is the difference? So, if we subtract it, so 12 by 60 minus 5 by 60 is equal to 7 by 60. 24 by 60 minus 14 by 60, this one, this value expected. So, 14 by 60 minus 24 by 60 minus the observed. So, this one minus this one, right, these two. So, 24 minus 14, 10, 36 minus 25, 11 by 60, 48 minus 41, 7 by 60, 60 by 60 minus 60 by 60 is 0, right. So, we got the difference. Now, you see which is the highest difference, where do you get the highest difference? The highest difference comes in the BCom case, right. The highest difference is coming in the BCom case. Okay. So, this test is calculated as D is equal to maximum of observed minus the theoretical. So, that gives us 11 by 60, right. So, this is equal to 0.183. Okay. So, 6 you can divide it and find out. Now, the table value of D at 5% level of significance. Now, significance level you can choose up to, that is up to your choice, right. This 5% level of significance is given by, now how much? Now, 1.36 upon root over of n. Now, 1.36 let us say is what you are getting. So, this value is coming to be how much? 0.175, right. So, since now this calculated value is 0.175. So, this means what? This is bigger or this is bigger? This is bigger, right. So, calculated value is bigger than the table value. So, what should you do in this case? So, is bigger, since it is bigger, it is coming away out of it. So, you reject the null. So, since calculated value is greater than the table value, Hence, we reject the null hypothesis and conclude that there is a difference among students of different streams in their intention of joining the club. So, this is what you do, it helps you to find out, right. Now, I will show you one more advantage of the case test. The case test is also used for normality checking. So, I will tell you how to do that, right. So, in SPSS you will see that so this is a case where what we have taken is there are few patients, right. So, diabetic patients, and these diabetic patients we have taken two groups of diabetic patients. One is 0 who are in some control, and the other is 1 who are in no control. So, they are eating whatever they like, they do whatever they like, so they are free, and the control group is one, they are under medication, they are doing some exercise and everything. The palpitation, so we feel that the doctors feel that because of the presence of diabetes, the palpitation, the heartbeat will change, will be more if it is higher diabetic. So, what we have done is we have taken the palpitation levels, right. So, now we want to check whether this is following a normal distribution or not, right. So, what we do is, so the case test helps you as it helps you into checking normality. So, how do you do that? So, go to analyze. Now, this is a non-parametric test. So, now let us go to the legacy, you can come to one sample case. Now, when you take the one sample case, right, so automatically you will see we have the palpitation, we have taken as the palpitation for the diabetes, right. So, what we go to options, so this is the descriptive we want. So, now the normal, this is the normal. So, we go for the statistics we are finding here is, you see the mean is 41, the palpitation mean for all controlled and uncontrolled is 41.13, the standard deviation is 11, the maximum and the minimum values are this, right. Now, from the one sample, so if you look at this value, it is giving you a significance value of 0.138. Now, when we say it is 0.138, what do you mean? That means the null hypothesis is to be accepted or rejected. The null hypothesis is to be accepted because it is bigger than or greater than 0.05. So, if it is greater than 0.05, you have to accept the null hypothesis. Then what is the null hypothesis in our case? The null hypothesis is that there is no difference between the data, right, there is no difference. So, that if there is no difference in the data set, then we will say it is same, right, the data set is more or less the same, and if it is more or less the same, it is like if you remember the Levin's, there is a test called the Levin's test for normality, right, in which homogeneity of variance, in which we assume that the homogeneity of variance between two groups would, if you want, if you are testing the homogeneity of variance, you expect the null hypothesis to be accepted and not rejected. So, normally when we talk about any hypothesis testing, we generally infer that the null hypothesis should be rejected, but when you talk about homogeneity of variance, you say that the null hypothesis should be accepted. Why? Because you want to test two groups and say that these two groups are comparable because they have a similar kind of a variance. Similarly, here when you talk about the the significance, if it is high, more than 0.05, that means we assume that this data is a normal data, right, it is a normal data and not normal. So, the normality assumption is accepted. Okay. So, that is why in the KS test we want that the it should be a more than 0.05 case if it is a 5% level of significance. So, that is coming true. So, this tells us that the data is a normal test. So, the KS test is largely used for checking this normalcy, right, and it is it is a very useful test, and you can do it yourself, and with some new data set you can take a data set and run it, right. So, we have understood this tests, all the tests. Now, I just want to make a recap of the summary of the hypothesis testing and we will wind up here. So, this is something that I wanted to tell you and you can use it later on. So, what happens when the sample is one sample, the application, the distribution is given to you, the level of scaling and everything is given to you. Now, what are the tests that you use? In the case of one sample and the it is a non-metric, the scale is non-metric. So, you use a KS, just one that now which we did, the Kolmogorov-Smirnov test and the chi-square for goodness of it, or you can also do a runs test for randomness, a binomial test for which similar to a McNamara test also. So, you can do that, but when it is a one sample and the data is in a metric, right. So, what you do is a t test, you do a t test if you know the variance, if your standard deviation and variance is unknown to you, then you do a t test, if it is known you do a z test. but in case of one sample and it is a metric, you do a Z test. So, let us just have a comparison and check the difference between the parametric and the non-parametric. In case of a 2 independent sample and it is non-metric, 2 independent sample, that means 2 different groups are there. So, we will use a KS2 sample test, or we can also use a Wilcoxon test, right. So, you can use a not Wilcoxon, the Mann-Whitney test, the Mann-Whitney test, right. Suppose you have 2 independent samples and it is metric, that means it is a more or less like a continuous, right. So, you use a 2 group test or a paired test, it is a independent sample t test, right. Now, 2 independent samples, but they are in proportions. So, it could be metric or non-metric, you can see. So, if it is metric, you have a Z test, but if it is non-metric, that means categorical, right, then we use a chi-square distribution or a chi-square test. You have 2 independent samples and they are in ordinal rankings, okay, and it is non-metric in nature, right. So, we use the Mann-Whitney U test, which is one of the most powerful than the normal median test, right. So, these are some of the tests that we are talking about, okay. So, you just see this difference you can make out. Now, here it is ordinal and here this is you sometimes you use the KS2 sample test or you can use the Mann-Whitney, but in this case if it is 2 independent samples. So, you use this mostly use this Mann-Whitney test, which is a more powerful test, okay. The last, if it is a paired sample and it is in metric, then you have a paired t test, okay. If it is a paired sample, but they are non-metric, then we talked about the McNamara test for binary variables or the chi-square test, right. Paired samples again ordinal. So, what you do non-metric is the Wilcoxon. Some of the things which I have even not present here, suppose for example, it is as I said it is 3 groups, for example 3 samples, right, 3 samples, then and it is metric, then ANOVA, okay. One sample, let us say, but thrice done, but thrice repeated, that means repeated and it is metric, then analysis of variance, one way analysis of variance with repeated measures. But suppose you have a one sample, let us say, and done repeated, but it is non-metric in nature. In such a condition, we use a Friedman's test, right. So, there is this is why I am explaining this to you is that you need to be very clear that you should not feel awkward that if my data is not normal, what will I do. In fact, in the real world many a times we see that the data might not follow a normal distribution, many times it will not follow a normal distribution, In that case, it does not mean you will stop progressing or moving ahead. Instead of that, you could use a non-parametric test for your benefit, but only thing is you need to understand in which case which test is optimum or the right test to be used, right. If you understand this, then your job would be easy and you can very well publish your papers, you can use it in your thesis writing, and you can do everything that is possible in a parametric test, that you can do it here, right. I hope I have tried to clear the non-parametric test part to you. I hope it will be clear, it is clear to you, but if you have any doubts you can surely put in your questions and ask, right, and I will try to answer them and as much as possible, because non-parametric tests are generally avoided by, I have seen people avoiding, that is my practical experience. So, but that does not matter. If it is if you do it, the more you do it, it will become simpler and more easier to you, and then you will feel much easier, right. Well, I hope this knowledge comes to your benefit and you use it well. Thank you so much. I wish you all the luck, right. Thank you so much.